Hi, good morning. Thanks so much for being here. I heard you had a fun night last night, so thanks for getting up and for having me. It's really great to be here and get to talk to you. Basically, the starting point of my work has always been around studying social systems computationally. And of course, society, nothing new. The people have been connected via some kind of small network for as long as humans have been around. But what's really changed recently is just the amount of data we have about these interactions and how this data is being used in the algorithms that facilitate this communication and these interactions between people and companies, between companies themselves. And what is going on is really an interplay. It's not just the mechanism of communication that has changed. What's happened is that these algorithms, especially with all this data that is now available, they are learning from people and adapting their behavior, changing how they work based on what information they have about people. And for me, the most interesting part is that the flip side is also true. Based on what algorithmic content is being shown to you or displayed to us, our behavior is also changing, both individually and collectively as a society. And it's really this interplay which is the focus of a lot of my work, and very recently looking at how this loop that forms can sometimes exacerbate societal biases that already exist, and seeing ways that we can figure out how to break this cycle, what algorithmic or optimization tools can we use that allow us to still facilitate all the fantastic things that technology has done without propagating or making all these societal problems any worse. So just to give a couple of examples of where these problems have shown up. And all of these have received some amount of media attention, and there's a lot of kind of articles out there if you want to learn more. But one recent study brought to light by ProPublica in the US was about the use of algorithmic decision-making in court cases. So judges in various states in the US have access to an algorithm which predicts for a criminal or potential criminal standing in front of them what is the likelihood that they will recommit a crime. And this information, this algorithmic prediction, is being used to decide who gets bail, for example, or who gets released on parole. So they're making these very big life-changing decisions for individuals. And various studies have shown that the algorithms that do this have biases. If depending on the person's profile, their ethnicity, their background, they will change the prediction. So this is one very clear example where an algorithm has basically picked up some of these biases that are in society due to context, due to history, and then are using them to predict outcomes that can have very negative consequences to individuals. Another recent example called the search engine manipulation effect has shown that based on the order in which you see articles, news articles about candidates, not even the content, just change the order in which you're presented with articles by a search engine, that can change your political preference. So that can potentially affect your vote in an election. And this was done in a few different countries, in the US, Australia, and India as well, showing how people can be influenced, again, just by the presentation order in a way that is strong enough to change their vote. Another example, kind of moving to the online space. So this is just a screenshot of the Wall Street Journal red feed, blue feed. If you haven't seen it, it's a fun little tool to play around with. What they do is they show you, for a variety of topics, this is the President Trump topic, what your news would look like on Facebook if you're very liberal versus if you're very conservative. So you can just scroll through this and you see that it's not just the leaning of the coverage that changes, the content is actually completely different. So that even the information that we see can be completely different from what our neighbor sees, depending on what these algorithms have learned about our personal ideas or preferences. And so this type of thing has led to completely polarized online spaces. A couple more examples. If you look at Google Images, so again, this was a recent study out of the University of Washington. If you search for various professions on Google Images, what is shown is actually a skewed gender representation of what is there in reality. So this is an example of an algorithm that's actually changing, in some sense, the ground truth. So if you look at this is CEOs. In the US, it's something like 27% of CEOs are women. In Europe, it's a little bit higher, close to 30%. And if you look at the top Google image searches, it's something like 11%. And this is true of every profession they looked at. Whatever the gender ratio actually is, the results skewed it more. So again, it's an example of an algorithm kind of learning some bias or some disproportion in the real world and exacerbating it. And what they showed in this study as well is that, again, this affects our perceptions. So if you go and you have seen these results, that affects your own idea of what the gender balance is in these professions. And as a last example, there's also a lot of studies on online advertising and how these, in the effort to personalize and target and show you ads that you're interested in, can also actually exacerbate biases. So things like ads for high-paying jobs are far less likely to be shown to women than they are to men. So in this case, you're just actually explicitly decreasing the opportunity for a lot of women because of, again, this thing that the algorithm has learned. It has learned that on average men make more money than women, and therefore it thinks that this slight difference means that men are more likely to click on this ad, and this gets turned into something that that can then skew what happens down the line. So overall, all of these examples, and there are many more, have come up recently as ways in which algorithms can basically increase discrimination. You can manipulate elections. There are polarizing opinions. And the question is really, what can we do about this? So as technologists, what can we do? And that's really what leads me to this question of questions of fairness or questions of diversity. And to start breaking down the problem, you have to think about where is this happening? Where is this arising? You can kind of think of this as breaking down into different places. So of course there's a real world, which, as we said, it comes with its history and its context and its own inherent biases. And what that means is, of course, that whenever we collect data, that data often is biased. Even if we had a perfect world, in that data collection process, we can end up biasing data. So that's the first step, where we start encoding these biases in the data itself. Then, of course, we have some algorithm that is learning from this data. And here, the important point to understand is that these algorithms can also introduce bias. So it's not just that they're kind of taking biased data and learning from it, but they can actually make that skew worse. Or even if you give them perfect data, they themselves can result in biased outcomes. And that's because of the optimization, effectively, that we put on top of it. So when we're building an algorithm, we have a purpose, right? We're not doing it for the sake of doing it. We have some goal in mind. And that goal, it might be a clear-cut technical goal, but in its interaction with the world can actually end up skewing things. And what happens is when you have these algorithmic biases, as I mentioned in these examples, this can feed back into the real world. It can change our perceptions, it can change outcomes. And it's this kind of vicious cycle that we want to break. So to give you the cartoon version of what I mean here, if we have, say, two populations of people, say we're a bank, we want to decide who to give a loan to. We have these people who have applied on this axis. Now, the distributions, again, in this cartoon version, are a little bit different because the real world is a little bit different. So that's this pre-existing bias. Now, technical bias might arise by coming up, by introducing something very simple. Say I just say the x-axis is income, and I just want a simple income cutoff. Right? That's a perfectly reasonable algorithm one could have. Of course, you can do much fancier things. But in conjunction, in this case, with the pre-existing bias in the data, what happens is if I just give everyone to the right of this cutoff line the loan, now the percentage of men versus women in this cartoon example that have received that low interest loan is higher. right? And this can feed back because, of course, if you get that loan, you have high earning potential. If you don't get that loan, then you have to maybe take out a high interest loan. Maybe you don't get to do what you want to do, and this is what feeds back into the real world. So what is the high-level goal here? There's now many people studying these problems, which is really exciting. The type of things that I do primarily are around detecting the bias, a large focus on developing the solutions, so actually looking at the algorithms, what can we do to break this cycle in that way. And then I also do a lot of work talking to companies, talking to policymakers, trying to see where we can get these algorithms used. But I think really, and one of the great things about being here and talking to all of you is that I think this is something that is really a message that that needs to be kind of embraced more widely by people who are writing code, who are developing software, who are doing research in data science or looking at all these things, because it's something that we really have to, I think, keep in mind as a culture, as a profession. It's not something that we can ignore, because just focusing on the technical side, we will be creating biased algorithms whether we want to or not. Right? So it's something very important for us to really think about as we move forward. Now, okay, I've been saying bias and fairness kind of interchangeably without really defining it. Partly this is because of many different ways of thinking about what that means very concretely. And really these ways can be broken down into two camps. So one camp thinks of things as individual fairness. So individual fairness is that if two individuals are identical except for what we call sensitive attributes, so their gender, their ethnicity, their sexual orientation, etc. So if two individuals are identical except for these specific kind of protected attributes, then the algorithm should treat them exactly the same. That's what it means to be individually fair. Now there's another camp that talks about group fairness. And what group fairness means is that when we have collections of people, say broken down by gender or broken down by ethnicity, when we have a group, each group as a whole should be treated the same as other groups. Right? So both of these kind of high-level definitions make sense, and they both seem like worthwhile things for our algorithms to have. The problem is that the two concepts are largely incompatible. There's some very strong impossibility results that say that unless your populations have kind of very specific distributions, you're not going to be able to satisfy both. And again, I'll give you just a very simple cartoon example of why this happens. Say you have kind of two populations. You have some red population and some blue population that are distributed slightly differently. Now, if you want to be individually fair, whatever you decide for these groups cannot take into account the color. It cannot take into account red or blue. So again, if we kind of think of some simple cutoff, or we can choose any process, I can't take red and blue into account or tailor it to either one. Otherwise, it wouldn't be individually fair. So if I say, okay, everyone above this cutoff line gets my loan, now you have this problem that I showed before, right, where you have far more blue people than red people here. If you say, okay, I don't think that's fair, I want to be group fair, I want the same percent of blue and red people, well, then by necessity, you have to have different cutoff values for the two. Right? So you're not going to be able to be both individually fair and group fair. Now, what is the right definition? I don't know. And this is kind of one of the key questions, or the first key question that you should think about whenever you're trying to design something for an application. What is the right notion of fairness in this particular context? And it will completely depend. I mean, I don't have a straightforward answer for you, and this is part of the fun, but also the challenge of thinking about these kind of problems. Right? In some contexts, maybe when we're dealing with humans, we really have to be individually fair. In many of the online contexts, I find that group fairness often works well because there we're talking about selecting content as opposed to selecting individuals. So I don't find so many scenarios in which it's problematic to have different treatments for different pieces of content. So largely, in a lot of the things I've done, I've focused on group fairness. And to tell you a little bit more precisely what that might look like, we can think of having some collection of content, and there's going to be some kind of selected set. So this is the set of content that I'm going to display on Facebook News, or I'm going to the set of images that I'm going to display to you. And what happens is this content, you can think of it as being broken down into groups. The group structure can be arbitrary, but for simplicity, let's say it's just a partition. So we have group 1 through group G, and you just partition the space into these different groups. And what these definitions boil down to is basically they're a function of the percentage of items from each group that end up getting selected into this set S. So if we let Pi be that percentage, now again there's kind of different notions of what it means to be fair, but roughly to be group fair, you want that percentage to be the same or roughly the same for all different groups. Okay, that's what it means to be group fair. Now within that, there's many different ways of doing that, of measuring how close is close enough, right? Or what is the right metric, or should I look at the percentage of groups, or how you split up these groups, or things like that. But for all these kind of very different notions, the good news is that there's more and more kind of fast, fair algorithms that are being developed. So there's more and more available algorithms that we can use. And of course, there's different approaches of doing this. But when I started kind of working in this area, I still found this a little bit unsatisfying that, okay, fine, there's a kind of impossibility result that means I have to focus on either individual fairness or group fairness for a particular application, that's fine. But within group fairness, there's all these different ways of measuring fairness, and what is the right way? Which again seems very context dependent. And finding a new algorithm for each application and each definition just seemed overwhelming. And it really seemed like we would end up in this kind of weird state where it's not clear what fairness is, who's deciding what fairness is, and who's deciding which are the right algorithms to develop. So the type of work that I've been doing along with my colleagues is trying to kind of go up a level and think of a more general framework for group constraints. So instead of giving a fixed definition and saying this is what it means to be fair, the type of algorithms that we have or that we're developing let you take in as input some constraints on these probabilities. So now for every PI, you can give me an upper and lower bound that says, okay, I need this PI to be within some certain range. And you give a different upper and lower bound, if you like, for each different group. Now what this lets you do is that if you have a certain definition of fairness that you need for your particular application, now it boils down to what is almost always a much simpler problem of translating your definition into the right upper and lower bound constraints. So that you can usually do very easily. So now for almost any type of fairness definition that you have, once you just have to worry about translating to the constraints, and we have algorithms that can help you achieve the goal that you want. Now, what is nice about these constraints is that, okay, as I said, they can satisfy all these different fairness metrics, but they're also very simple, right? These are convex constraints, and not even a difficult convex body. They're just very simple box-like constraints. And what that's going to let us do is also develop a lot of fast algorithms, because as soon as we want to do this at scale, we really need something fast. Okay. So let me give you two examples of where we've done this. One example is personalization, or personalized content. So again, the cartoon version of this is, of course, we have a whole bunch of content. Let's say there's two types of content, red and blue. And our algorithm is going to select from this content to show on your feed. So on your Facebook feed, news feed, whatever it might be. Now, of course, these personalized algorithms, they're constantly learning about you. Right? So they're seeing what you like, what you don't like, what you read, what you click on, what you hover over. And all this information is being fed back. And the more and more the algorithm learns about you, the more and more personalized your feed becomes. So again, the cartoon version is that we're just thinking of each person as some point in some high-dimensional space, and depending on what they like in this feed, that image of this person or that representation of this person is moving. And of course, what leads us to this red feed, blue feed phenomenon is that as we learn, we just allow you to move more and more into the corners of the space. Right? So eventually what we're seeing are completely different types of content. So what are these constraints in this cartoon version? It's basically just a little fence. So we're not letting you just reach these extremes. So again, this is something very simple that for most algorithms, it's basically a very easy cutoff point or throttle that you can add on to make sure that you don't over-personalize. To be a bit more concrete, one of the ways in which personalization can be done is via these multi-arm-bandit type of problems where you have these key arms which correspond to your types of content, and basically what this algorithm is doing is maintaining a probability distribution. This is just kind of this point in this space as to what it thinks that you like, right? And every time, of course, it has to select some content to show you, and then it receives what is in this language called the reward, which is how much you liked it, right? Did you like it? Did you read it? Did you just scroll past it? And what these algorithms do is try to figure out what is the ideal arm, what is your perfect type of content, right? What is your favorite type of content? And what it does is it tries to learn this, and how well it learns is measured by regret. But it tries to learn this, and then once it learns this, it will basically just always show you that type of content. And that's, again, what leads us to this type of polarization. Now, what these algorithms are trading off is what's called the balance between exploration and exploitation. Exploration means kind of testing different things out in case there's something else that you like that we missed out on. And exploitation is actually just showing you what you like a lot. Right? So again, to give some cartoon version, if you have all these different content here represented by people that you're trying to select, okay, at each time step I choose something. If you like it, then I'm going to end up putting more probability mass on there. In fact, I put almost all the probability mass on there. This is a simple algorithm, but many multi-arm-bandit algorithms roughly think of it this way. So with most of the probability mass, I just put it on the best option so far, and then with a small probability mass, I put it on everyone else. And as I keep selecting content, I keep changing who I think is better, what the best option is, but overall, it always ends up like this. Right, so eventually what happens over time is that you converge to something, and now it's not just that type of content, but that one specific type of content gets most of the probability mass. So what is the solution? Basically, again, it's just a small tweak on this algorithm. So what these constraints mean in this setting is that the probability mass on any particular group or type of content has to be constrained within these upper and lower bounds that we have defined or can take as input. So say, okay, I can only put kind of between 5 and 10 of these blocks of probability mass in there, or whatever it is that your constraints are going to be. And now the goal has changed, right? Instead of finding kind of the one type of content that you like the most, now I still want to maintain a probability distribution. I'm not worried about zeroing in on one type of content. I'm happy with the probability distribution over content. And the constraint here is that we have to balance the probability mass across groups. And within that, we still optimize. So we still want to get the most reward. We still want you to like it as much as possible, but we have to maintain that balance, right? So again, you have to kind of change the notion of regret a little bit, because now we're thinking about this kind of fair optimal solution that we compare against. But the goal is still just to learn what that is. And again, we want to do this, of course, with kind of very fast and low regret algorithms to do this. So, so what we can do here is, again, just tweak the algorithm a little bit. So before, again, we had that kind of best arm that we were selecting with a high probability mass. Now, instead of doing that with a high probability mass, we select from the empirical optimal based on what we've seen so far. Right? So we have some kind of Q hat, which is what we think is optimal based on what we've seen. And with high probability, we select from that. And then with a small amount, we still do our exploration. We still test out other things. Again, what does this look like? This is what it was before. And if you break down by groups, this is the amount of probability mass, we have just added on these constraints, which means that which means that the original solution was not what we wanted, right? So basically, these red ones are over. We put too much mass now on this particular blue type of content. Now the question is, what is the right probability distribution? And finding this Q hat is not always easy. It depends on the group structure. But in this case, if you have a partition, it's actually very simple. And what you can do is basically just a greedy algorithm where you look at what is the highest, what is the next highest piece of content, and then you try to put it there. So you just go to the next highest piece of content and put it there. Now, if this content was blue, that wouldn't work for us, right? Because it would still be blue, so we'd have to move on to the next person. But we keep doing that until we find a distribution that works, and you can prove that this is optimal. So indeed, you can show this optimal. It's as fast as we can do it, and there's some very nice new fast optimization techniques that even let you do something very similar when the group structure is much more complicated. Okay, so another to give another example from online systems is ranking. So everything ends up getting ranked. So you have a bunch of images. You want to order these in some kind of ranking that you're going to display online. And basically, now each image has some kind of utility that the user gets from seeing that image in a particular location. Okay, so the goal generally is to basically maximize this utility. Now again, there are many different ways of defining the utility and many different algorithms for doing it, but largely most algorithms boil down to this. Now the question is, what should this order be? And this also kind of ties back into the search engine manipulation effect paper that I mentioned, that just that even if you have the same items, just changing the presentation order can change perceptions. Right? Okay, so again here we have to think of what are the constraints, what constraints make sense in this setting. Basically what the constraints mean are just upper bounds on the number of individuals from any particular group that can appear in the top K positions. Right? So if you go down the list, you want to make sure that for every K there's some maximum amount from any particular group that can show up there. So if these are say our people across the top, and these are positions A through F, this matrix represents these utilities, these weights of putting this particular person in a particular location. And here, just by the way I've arranged the numbers, it's okay, and then you can have your upper bounds, right? So based on how these numbers work out, if our goal is, of course, to find a ranking that maximizes this overall utility, well, the first thing that we could do is just, again, try to do this greedily. But if we just try to do that, which corresponds to kind of taking this diagonal in this matrix, we soon run into a problem, right, where we violate this constraint. As we start, we're fine. At first, there's one blue person, there's two blue people, and one yellow person. But now at this fourth position, we run into a problem. We don't want more than two of any particular group, and we have three blue people. So what do we have to do? We have to do something a little bit different. But what we can do is actually very simple. Again, there's a very simple greedy algorithm that works, where we just try to work our way down this diagonal. And as soon as there's a problem, right, as soon as the next person that we would add in will create a violation of these constraints, we just keep working our way down the line until we find someone who does not violate the constraints. And then we try to go back to this diagonal and keep working our way down. Okay? So this is another example where, again, it's something very simple. It's a very simple greedy algorithm. And the reason why this works is really because these constraints we have, as I said, they're so nice. Right? If you look at arbitrary constraints in this problem, you could say, okay, from in position 1 and 5 and 7, I want this. In position 3 and 4 and whatnot, we want that. But that doesn't make sense in the fairness context. What the type of constraints that make sense here are really amenable to these kind of very nice, fast, greedy algorithms. Okay, so those were just two examples, but we've been looking at a whole bunch of different ways of thinking about this problem and different algorithms and seeing when and how we can basically come up with these fast solutions. So again, things like sampling, when you're kind of subsampling data, or selecting things for image search, personalization, which includes Facebook and Google News, ranking, where you can also look at hiring or crowdsourcing. A fun one we've been doing lately is voting. So actually in Switzerland, they have one of the cantons, effectively one of the states, is rewriting their constitution. So they're trying to decide which committee should rewrite it, and they want this committee to be balanced, which I think is fantastic, right? So they want it to have representation from many different people, many different types of people. So they're actually going to use this to, as part of that election process, to make sure that the committee that is selected is balanced or is fair. So the take-home here is really, in some sense, like how can you avoid reinventing the wheel? If you look at all of these problems, it's basically a constrained version of something that already exists. Right? You don't have to come up with a brand new algorithm. There's just some very simple constraints added on top of them, and often things already work. So often you'll have kind of a constrained optimization toolkit that you can use right away. And if that's not fast enough, because those are often overkill for the simple constraints that we have, often just a very simple greedy algorithm will work. So again, the key take-home here is just think about these problems. Try to not reinvent the wheel. See what you can use that is already there. This should not be kind of an overwhelming prospect. I think a lot of companies like to have us think that, they really wish they could be fair, or they really wish they could be unbiased, but there's all these technical hurdles. I'm not buying it. And I don't think you should either. I think that often there's many things that we can do if we have the intention to do it. Okay, so one thing that you might have noticed in that example I gave, or that you would quickly come to if you start thinking about these things, is that, okay, but if I was trying to optimize something, and now I start putting constraints on it, then my end result is not going to be as good. So this is really the main objection that companies will have. That, okay, how will this hit the bottom line? Because that's not something that they would want to happen. So here's just one example for personalization, where we looked at an existing data set that had a bunch of articles. They were kind of split up into different groups in terms of types of content, like sports and entertainment and politics and world politics, things like that. And we had explicit data from a variety of users that were reading these articles and giving explicit ratings. So we were using this as a kind of underlying ground truth. And we ran some counterfactual experiments looking at the different by varying the constraints and measuring the performance in this personalization setting. So here, the y-axis is the performance, so higher is better, and the x-axis is the constraints. So on the far left, these are no constraints. Weakest means we don't place any constraint. And on the far right, it's the tightest possible constraints, which means that we force exactly 1/8 of content from each group. So that's the tightest type of constraint you could have in this setting. So what we talked about before, and what our algorithm, what is provable, the result in the algorithm, is that the regret is small. Regret is just the difference between what our algorithm, which is this red line, can do, as opposed to the optimal, which is before we learn, right? If we knew everything ahead of time, what we should do. So this gap is indeed small, as expected, and we can't do better than that. But what I'm talking about here is this gap. So what is the gap between the unconstrained optimal and how much it's even possible for us to get when we add these fairness constraints? So here there's a gap, and actually I chose this particular experiment in this particular data set to show you because out of all the data that I've looked at and all the experiments that we've looked at in all of these different platforms, this is actually the one where it's the worst. In many cases, this gap is inexistent. And really what's happening is that, so this gap can be there in the worst case, right? So it could be that there's only one type of content that you like, and you like it way more than everything else, and I put constraints so hard on it that you never get to see that. Right? Now, okay, so this is a worst case example, and this gap is going to be huge in that case. But data is rarely worst case, right, as you all know. And what ends up happening is that usually from all groups, or most all groups, there will be some piece of content that you would still like, for the most part, right? And so what happens is that this distribution of data across groups is not so different. We have so much data, there's so much news online, there's so many Facebook stories that we could possibly show you, that there will be something that we can show you that satisfies the constraints, and you like almost as much, right? And that's really what we see the more and more we start digging into this data. So that's also something to keep in mind. Don't be kind of scared that this is going to hurt the bottom line. Often it doesn't. Often we don't even see any gap here. Now, from the theoretical point of view, because I was at least initially a theoretician, of course we would also want some formal guarantees on this price of fairness. This is something else that we've been working on. For some problems we have it, and some problems we don't. But basically the question is, what properties of the data can we measure that would then guarantee that we have a small price of fairness? And this is, again, something we've been working on. For some problems, we can actually even prove to you that this gap is going to be negligible for the data that you have. Okay. So I just want to kind of pivot a little bit to look at some other experiments which will relate to these type of metrics, or relate to how we're measuring this bottom line. So this is one study we conducted a few years ago. We were looking at MOOCs, these massive open online courses. And we had two MOOCs we were looking at. One was Intro to Art and Intro to CS. And we were looking at different ways of, again, ranking content, in this case in the forums. So there were a bunch of forums where people could post a question, right? This is some question. And then there were answers. So people would answer the multiple choice question and write a little blurb about it. And as in many forums here, there were also upvotes that were being displayed. And our original question, we wanted to understand how the different mechanisms for basically collecting information from users as to how to rank data. So as kind of our ideal benchmark initially, we looked at kind of a curated ranking. So this was a professor explicitly went through and ranked these answers. We had a social condition, which is this one that you see here, where people can upvote, and then we also show you how many upvotes each answer had. We had a non-social condition where people can still upvote, but basically these green boxes weren't there. So you couldn't see the numbers of how many people had upvoted each one. And of course we had this kind of random baseline where we just ordered things randomly. So what did we learn here? So the first thing that we looked at, we had some independent experts grade each answer, and then we looked at the top of the ranking. Here I'm showing you for the top three. And we said, okay, what is the average grade that these top answers had for these 4 different types of rankings? So perhaps unsurprisingly, in both courses, if you look at the curated, right, the ones that the professor ordered that had the highest grade. If you're familiar with this area, it's also not surprising that the non-social condition had the second highest grade, because as soon as you have social, then things you can have herding and things like that, and sometimes you end up with some suboptimal solutions. Followed by social, and of course random was last. So this is all was as expected. But then we thought about, okay, well, what if we kind of measure how good these rankings are a little bit differently? Instead of looking at these experts, we looked at the students themselves, and we looked at their performance in the quiz at the end of the week. Right, so how well are they performing in their quiz when they were exposed to these various conditions? And here completely switched it around. We were actually quite surprised to see that the social condition was actually the best in both cases. And perhaps a little bit embarrassingly, the random condition was quite good in the art course, even better than what the professors had done. So, of course, the first thing we did was check everything and know there was no bug. And the second thing we did was sit down and think, okay, well, how is this possible? Why is random doing so well here? What changed? And what we realized is that basically, even though kind of objectively, if you look at these answers individually, they're on average lower in quality, they're also much more diverse. So the type of answers that the social condition was surfacing were quite different from each other, right? Whereas if you look at which answers the professor thought was best, they were largely very similar, right? So the point here is that what we were missing in this first metric was that we were not really looking at kind of the collective information that was being given by the top of a list. And if you look at the collective information, then diversity is, of course, a very good thing to have. Right? It's not useful to read the same answer rephrased a different way. What's useful is to hear a different point, or maybe an answer that's not as complete but raises something new. And this is what we see evidenced in the second metric. So the same way that what is fairness, what is diversity, there's again different ways of looking at it, but basically you can think of different groups of answers. You have different types of answers. This is a real question from Cora, I think. How many eggs are in a dozen? Okay, if you look at the kind of quality-based ranking, you might end up again with kind of the same information at the top. If you look at a diverse ranking, the idea is that you have different types of information and you kind of see a little bit of everything near the top. So this was another study we did on various Stack Exchange sites where we looked at kind of the ranking that has the most amount of diversity. And by, again, looking at these different, basically, we took all of the answers, they were classified into different groups, and the maximally diverse ranking would just kind of round robin across, choosing one answer from every group. Within a type, it would sort by quality. And we compared the Stack Overflow ranking, which was already being done by upvotes. So it was already more diverse than kind of this quality-only ranking, but not as diverse as our diverse ranking. And here we conducted a bunch of experiments on Amazon Mechanical Turk where we're asking the user, okay, which of these rankings do you prefer? And again, what we saw was that largely the users for the various different Stack Exchanges still preferred our diverse ranking. Now here we didn't optimize anything. It's maximally diverse is probably, or is perhaps too diverse. I don't know. We have to go back and look at this a little bit more. But generally, what we saw was that this adding more diversity, even more than what the upvotes were already getting, was a positive thing. It resulted in a more positive user experience. So again, if you just look at the quality as measured by, again, either by outside experts or the quality as measured by the number of upvotes at the top of the list, this is decreasing your quality, but overall it is improving user satisfaction. So these three things really lead me to this question of, are you using the right metrics? Right? So as we saw, okay, this gap could be there. Generally, we don't even tend to see it. We have to think a little bit about what are the metrics that we're using. In the end, whenever we're designing these applications, what we want is largely to increase user satisfaction, right? That's what will keep people coming back. That's what we want to do on some level. And there are some, I guess, fairly standard ways of doing it, fairly standard metrics of measuring this, but that's still just an approximation. Right? And I find that largely these approximations are also designed with some constraints in that they should be kind of relatively fast and relatively easy to compute. And because we need them to be fast and easy to compute, they tend to break down the problem into these individual components, right? Looking at each answer individually, finding a grade, and taking an average, right? That's easy. If you have to measure how good something is collectively with every group as you add each piece of content, then things can become more complicated, although there are more and more metrics that are doing this. So are you using the right metrics? Do they capture diversity? And how much does diversity impact the quality of the result, how much the users like your results, and how much they're coming back? Okay. Okay, so I think there's still a lot to do here. I've talked a little bit about some of the problems that we've seen, the areas where we've seen problems, and some of the algorithms that we've developed. But this is still kind of just one piece of the larger puzzle. I think there's a lot of things that I kind of brushed under the rug in order to be able to get to tell you about some of the interesting things that we've been doing. But I think there's a lot of really core interesting problems that I hope some of you can help us tackle. I think one of the key questions is how can we automate these processes? All right, so how can we detect bias in an automated way? We can't count on waiting for a journalist to go find some problem in some algorithm that's being used for the public, making a big fuss about it and getting it all over the news, and then a couple of computer science start studying it. It's not an efficient way of doing things. So how can we actually go find ways to build this automatic detection into our algorithm where we start measuring the behavior of the algorithm as it is running, as it is learning, as it is changing? I think another very difficult question is how to define the groups. So what are the groups that we want to be fair across? Right? If you're talking about something like this parole case, then that is a little bit more well-defined. As a society, we are governments, we have kind of agreed upon certain attributes of people that we're not allowed to discriminate against, so our algorithm should not discriminate according to those features. Right? So that one is a little bit more straightforward. But in this online space, it's no longer clear, right? When I show this this example of images, should we just care about gender? Should we care about ethnicity? How do we even tell from an image sometimes? So trying to understand what are these groups that we should be fair across, and also finding ways to efficiently learn the group membership properties of content is another kind of very important open question, which I don't have a good answer to. Of course, there's a lot of more work to do around algorithmic solutions, things like what I talked about today. There's so many other problems or applications where we can try to apply this framework to. I'm just one person. We have a small team, so we're doing as much as we can. But the more the merrier. I'm definitely happy to talk to anybody if we have some particular problem in mind. And there's also this other kind of largely open question, which I pointed out, about proving formal guarantees. Right? So when can we actually show that this price of fairness is small? And even if we can't show it small, what are the right metrics to use here? So how can we define the metrics that really capture this more holistic approach to studying the quality of our algorithm's output? Another point that I think is difficult is, of course, getting this deployed. So, as I mentioned, we've been talking to a bunch of policymakers. I'm in Switzerland, so it's nice to be close to Geneva. So there's a lot of interest from the UN and all these other regulatory agencies, basically thinking about, okay, what even makes sense? So, like, does it make sense to regulate algorithms? What would it mean to regulate algorithms with respect to fairness? Of course, there's already the GDPR, which is doing all kinds of perhaps positive, perhaps some negative as well, things related to privacy on a global level. So what would that look like for fairness? And I think it is so crucial that technologists actually talk to regulatory agencies. Otherwise, it'll end up being pretty meaningless, anything that one can come up with. So I really encourage you also to just go out and talk to as many non-CS related people as you can. Because it also gives you a very interesting, a very different perspective. Sometimes we do end up in our bubble. I've definitely been guilty of this, where we're kind of in the trenches of kind of digging through some data or trying to come up with some technical solution. And she's saying, okay, what even makes sense as a definition of fairness? What even makes sense as something that is even possible to regulate? And of course, the last thing is studying the impact. So we're still kind of in the early stages of these. I'm at a university, so we have a few kind of little small demos for a bunch of this work that we've done, but it would be really great to see this actually being used in companies, actually being used on real users, actually looking at that data and seeing what difference it makes. Is this bringing users back? How do they interact with the system differently? What are kind of the long-term effects on their behavior, on their opinions, and things like that? Thanks. I think I finished right on time. It was great getting to talk to you guys, and I'm really happy that we'll have a Q&A session. So please do come. I'd love to hear your perspective and get a chance to talk a bit more.
I thought maybe to take one question here. Sure. To kind of start kicking off the discussion. So you were asking yesterday.
Thanks. So apparently handing an arts expert a bunch of random posts about an image doesn't really change the quality as gauged by experts, whereas in computer science it does very strongly. Did I understand the image you showed about the ratings and the ratings by other experts, so that in the arts field, like handing a set of experts, so the top picture, handing a set of experts some random posts and letting them sort them in a certain way doesn't really change the quality of the overall set of the text, whereas in computer science it does change the perceived quality a lot. So I compare the purple bars versus the red bars. So my question is, are there certain fields in the news or something where there might be a latent fear that being fair might reduce the quality of the news a lot, whereas in others apparently it doesn't really affect it? If you say that the random bar is kind of fair or diverse versus the curated is very much focusing on a certain group.
I see. Yeah. So here the difference was, so here you're, I guess, pointing out the difference between the art and the computer science, that in one they were kind of the same, whereas in the other there's a gap here. I think here, so in this particular study, what we saw is that basically this computer science course was harder, and there were many answers that were just flat out incorrect. So if you randomize and put incorrect answers at the top, then that's going to affect your quiz scores. Whereas for art, most of the answers were mostly correct. So that's why there was a gap here. So that's definitely something that would be, in this case, course dependent. I think your broader question is very interesting. That is it, do we have to think about in some sense, based on the field, when it makes sense to be more diverse or not? And what you proposed was basically, if kind of random is already diverse, then maybe it's okay to diversify. Yeah, that's an interesting way of looking at it. I think one thing that this framework lets you do is that what you can do is basically place constraints so that you push everything towards fairness by an epsilon amount. So that might be one way to do this, so that, okay, everything becomes a little bit more fair, but it's not too far from what you were doing anyways. So that's possibly one way to do it, if that's what you would like to try.
Yeah, okay, thanks.
Thanks.